Consider the height as I move from 1, 0. In the beginning, it increases very quickly. But as I rotate, the height begins to slow down until I hit the 1, and then I slowly decrease before essentially dropping off very quickly in a pitfall. In the same way, you will see once we explore our sine curve that in the beginning, I gain in y value very quickly, and then I slowly taper off until I hit my maximum. Then I slowly decrease, increasing in speed, and then I continue in that same pattern, slowing down at -1 and coming back. And this is going to happen again and again and again. Like this little funky curvature is going to repeat again and again and again. This funky looking curve is what we call a sinusoidal function by definition. Okay? It's basically using a sine or a cosine as the parent function, and what we do with it you'll see much later. Today we're going to explore what it looks like, what do these things mean, how does that translate to real life, so on and so forth. We're trying to get familiar with that. Okay? So I have an activity for you. I'd like you to bust out your, take out your sheets. I hope you took one from class. I forget if I told you to take one. We're going to watch a quick video of a Ferris wheel rotating. Your goal is to observe it. Please observe it. Where's my mouse? I would like you to observe. Jeez, I can't even. Okay. Please observe and tell me what are some details you can pull out of it. There isn't much, right? There's very little. You're just going to see a Ferris wheel. That was weird. Can you still hear me?
Yeah.
Okay, that was really weird. I don't know what happened, but my headset just sort of died. Interesting. Oh, I think I know what happened. All right, never mind. As long as you can hear me. Um, Here we go. I'm going to ask you, what do you observe? What could you measure? And see if you can model something. I'm gonna show you in just a second. Okay. I have for you this video. It's super exciting. Clearly, I have like the most entertaining things for you. Okay. As you see, this video shows a Ferris wheel, and I would like you to follow the movements of the red uh, cart. Okay, so I'm going to share the sound. It might get really loud, so you might want to put down the volume a little bit. Please take a look and see what details you can pull out. Things like how long it takes to circle, how high and how low it goes. Consider the speed. In the very beginning, the first maybe 10 seconds, the speed is really slow, but ignore that. Pretend the rotation is all a constant speed. Okay? Figure out how long it takes to rotate around and also what you notice about the heights. Ready? And go. Whoa. Okay. Wonder if you saw that. Okay. What do you notice about, I guess, its movements? What do you notice about its height? Can you draw the movement on this curve? I'm going to show you one more time. See if you can figure out what that would be, what movement it would be. And then as a clue, if you look at the bottom, we're going to talk about why the 3 underneath will not be an accurate depiction. I'll show you one more time. Sharing and go. That's it. That's all I have for you. Draw it out. Um, and try to draw like a full cycle of it. As in, if I start at the bottom, if I started my Ferris wheel at the bottom, draw what it would look like until it returns back to the bottom. Okay. Going once, going twice. Here's what I'm hoping that you're able to capture. First, you notice that my cart starts slightly elevated from the ground. And it's red, so I'm going to draw it in red. Okay, so this is actually your start point when time is 0 seconds. Also notice at a certain point in time, I am going to reach the highest point, and then at a certain point in time, I'm actually going to come back. As you might notice, the speed at which we rotate is exactly the same. So the amount of time it took for me to get to the top and the time for me to return back to the bottom should be equal. So Ian's got something on chat saying from the start point, a curvy line going up and down slowly, then repeating. Yeah, it's really hard to describe though. What I also want to mention is between the maximum height and the minimum height, right? Because that's minimum. The Ferris wheel isn't going to crash into the ground. This is as low as the Ferris wheel could possibly go. At the middle, we will always pass the middle to get to the top and the bottom. So from here, I pass the middle, I get to the top, and then I pass the middle and I get to the bottom. So somewhere between the lowest point and the highest point, directly in the middle should be another point. Same thing here. The highest point and the lowest point, between the two, there should be a point. And lo and behold, I'm back at the lowest point, which means I'll probably repeat the same movements again and again and again, because this is a circle after all. At this point in time, you might also, again, be very tempted to draw straight lines, but that is not a correct curve, as you might have noticed from us discussing why this first graph right here is not going to be correct. Okay, so that was a clue. Since I changed the dimensions, my markings are off, so let me just move that over. Okay, continuing on. So if it's not a curve, what is a good way to describe it? Well, being a perfect circle, I'm going to give you a suggestion. It's going to, from the middle, it's going to be a perfect circle, and it's going to be a perfect circle. In other words, the top half and the bottom half are going to be symmetrical. The easiest way to do that is using the middle points. Just connect it as if you were drawing a parabola, but stop where the 2 points are. And then draw something that might look like a parabola, and then stop. A curve, half circle, stop. So on and so forth. Okay? And if this continued in the negative time direction, I have a little dotted line there to show what it would look like. But of course, we're not interested in negative time, so we're going to just end there. Did everyone get a chance to see how much time it actually takes to do a full circle? Oh yeah, Lucas, how did you get that? Lucas says that full circle is 40 seconds. How'd you know? Halfway to the top, in other words, from 0 seconds to get to this point right here, which is a quarter of my full cycle, 1/4 of my cycle is 10 seconds. So if I go at the same speed to get to the next half, it would have been another 10 seconds, which is 20. To get back to the middle, it would be 30 seconds. And to get back to where we started would then be 40 seconds. That's absolutely right. So in this particular case, we say that a period, in other words, another way of saying the time for a full cycle, is 40 seconds. It's good. So I think this is as far as we can go in terms of pulling out information. What do you notice then? What can you say about the three different examples on the bottom and what's wrong with them? What can you say about the first one, the pointy one? Why is that so wrong? Mhm. So without getting too mathematical, you can say that what's wrong is there's no gradual increase decrease. It's literally sort of like a very jerky. If this was a car ride, you would get motion sickness. You'd probably throw up. Okay, it's just like a constant ride. It's like, and then without even slowing down, it just like jerks back and goes in the opposite direction. Boom. It's very jerky. Okay, so that would not match up with my Ferris wheel. Ferris wheel, there's no jerkiness involved. It's just smooth up and down. Okay, so maybe you can say there is no gradual increase or decrease in height. I guess you can say that. Okay, too pointy, there's no curves. Next one might be a little easier to explain. What is wrong with the second one? Not symmetrical. True, but why do we care whether it's symmetrical or not? Not the same height. Also true. Why does it have to be symmetrical? You're right, but I'd like you to explain. If it's a circle, it would be the same height. Right. So a circle, like a Ferris wheel, doesn't like have full movement, right? It's just fixed on the ground and it just rotates, which means, yeah, the movement has to repeat again and again and again. That's the whole point of a sinusoidal. It's a repeating motion. What's also interesting about this one is I'm starting my Ferris wheel here, but I never return to that height. It's like the cart took off somewhere and it flew off. And it's going back in a weird bouncing direction. It's a little scary, right? Same with the max height. Max height was set here, but then the next time we go up, height changes. That doesn't make any sense. Okay, so for this one, we can say something like max min is not constant. That's what's wrong. How about the last one? I think I alluded to it already, but someone want to mention this one. I'll take over. Long story short, yes, it's inconsistent speed. The whole point is that the motion is repetitive, it's periodic, it's repeating. If I say this is my lowest point, here's my lowest point. The time it took to get from what to complete one cycle was here. But from the highest point to what I'm going to say the highest point is around here, clearly it's not a repeating movement. Sometimes it's fast, sometimes it's really slow. That's not periodic. There is no period. There's no repeating period. So there it is. Okay. While you're copying that, I'm actually going to move to the bottom of the next questions. Where will the cart be after exactly 3 minutes? 3 minutes being 180 seconds. Recall, one period was 40 seconds for one cycle. So where would I be? Here's a quick piece you can do. 80 divided by 40, that gives me 4.5 revolutions. So yeah, if I start here, 4.5 revolutions means one full cycle, two full cycles, three full cycles, four full cycles, and then half a cycle. After 180 seconds, I will be at the top of the Ferris wheel. And this prediction right here, what if I asked you for, 3.25 minutes, 1.117 minutes? If numbers that I give you are obscure, it might be useful to have an equation that you can plug numbers into, right? And that's sort of our goal. We're trying to take a sine function or a sine curve and apply it and create equations out of it, okay? So all this other stuff that we've put in here, I don't think you have to worry about because I'm going to show you in just a second. I'm going to rush through it because of our time issues. Number 6 also, it's not something you have to worry about. I tried to explain where this is coming, but I sort of alluded to it through our minds on. For now, I like you to just, read at your leisure, okay? You don't have to worry too much about the finer details of this. You are going to see it in action anyways. All right, so I'm just going to skip it. Don't worry about it. So just skip that. Um, Now that we are slowly getting introduced to sinusoidal functions, so sine functions and cos functions, I'm going to be using certain words that help me describe functions a lot easier in this unit. For example, you've already seen me use the words period. I'm going to be referring to amplitude, and I'm going to talk about a periodic function to mention how a pattern keeps on repeating. So all you have to do is figure out one phase and you're done. Let's reiterate. Let's add some of these terms onto a graph so that you understand what I mean. For a period, typically this is going to be 1 and -1. You don't have to. For a period, I am looking to complete one cycle and see how long that's supposed to take. So let's pretend I start here, and you notice the curve I'm moving upwards. The next time I'm at that same location is not here because right now I'm moving downwards. The next time I'm in the same location moving back upwards is right there. In other words, from this point to that point on the graph is considered one period. Another way you can look at it is forget the midline. You can maybe go from the maximum point and check the next maximum point. You can say this is also one period. It doesn't matter where you start, as long as you complete one cycle, that is going to be my one period. As a quick, quick refresher, how many degrees will be considered one period for a sine or cosine function by default? That was fast. 360. That was really, really fast. Yeah. So by default, the typical unchanged period is 360. Okay? But this, of course, once we start doing things like transformations, is going to change. We can manipulate this. That's tomorrow. Let's keep moving. Another word you're going to see often is the amplitude and, of course, the mid-axis. Consider this wave as if it was literally like a wave in the ocean. If there was absolutely no wind and the water was completely calm, the up and the down would average out and hit this surface of this sea level. At sea level, we're going to call just the mid-axis. Some textbooks may call it a central axis. Some places might call it just the midline. Um, Either one is okay. I'm all right with either one because it makes sense to me. The amplitude would be the vertical distance away from that mid-axis. So here and here, these are called amplitude. Okay. By default, we never say the amplitude is negative. We just say that amplitude is just the positive number. So if this is going up to a +1 and this goes down to a -1, right? Depending on which part you look at, you can say the amplitude is 1 or -1, right? So just to keep this consistent and keep things from getting confused, we just say that the amplitude is 1. I go up by 1 or down by 1. The value is 1, the absolute value. Okay, the value is 1. Any questions so far? Going once, going twice. Okay. Well, let's keep moving then. I am going to now look at what a sine and a cosine curve looks like. We're going to draw it out, and that will set or prime us, get us ready for the quick optional assignment that I'm assigning to you. All right? Let's clear this. Let's move on to section 5.2. Now, I'm sorry that if you took my sheet and it's very small, I want to save paper, so I printed these in 2-in-1. Okay? But it should be okay. I think we'd be able to do it. Now, I don't have that much space, so I'm gonna try to squeeze all this in. Perfect. Let's get an axis in there. Oh, shoot. Right in the center. And then I need to go in the positive and negative direction. So somewhere in the middle, somewhere here, I'm going to have the axis. Follow along with me. In this case, my x-axis is going to be theta because it's dealing with an angle. And the y is just some value. Everyone with me? All right. Let's see how much you remember of your special triangles. I think it's wise to have 3 squares equal 90, so each box is 30. That's 270 and 360. In the negative direction, that's negative 90, negative 180, negative 270, and negative 360. Also, let's make 3 boxes equal to 1 and 3 boxes equal to negative 1 in the y direction. I'll just give you like 30 seconds. All right. All right. Consider, once again, my sine function. My sine is basically y over r. And so I'm basically asking you to tell me what the y value is when my theta is 0. What was it again? When the angle is 0, what's my y value for this point? Sorry, what's my what's my y value for this point? Chat says 0. Thank you. So at 0 degrees, my y value is a 0. If I rotate my terminal arm and I am now at 90 degrees, what's my y value? Somebody?
1.
Good. And if I rotate 180 degrees and my point is now here, what's my y value? 0. And then I rotate 270, what's my y value? Negative 1. And then if I rotate all the way back to my starting point, my y value becomes a 0. Does that change if I rotate the other way? Let's take a look. Let's say I rotate a negative 90 degrees. What is my y value here? Suddenly it's weird. It is a negative 1. If I rotate a negative 90 degrees, what's my y value here? 0. If I rotate a negative 270 degrees, what's my y value? It's going to be 1. And when I come back negative 360 degrees, it's coterminal with 0, so it's going to be there. Do you see something interesting happening? Oh my goodness, it's a repetition. Coincidence? Nah, This is the whole point of sinusoidal functions. It's a repetitive movement. Okay. Let's see how much you remember of your special triangles now. Oh, you know what? Hold that thought. Let's draw it in. 0, 90 gives me 1, 180 gives me 0, 270 is -1, and 360 is 0. And going backwards, -90 is -1, -180 is 0, -270 gave me this, and -360 gave me that. Yes, we're going to draw a circle, and you can cheat and draw it in, but just for this one time, I'd like you to walk through with me. Sine of 30 degrees. Going once, going twice. Half. If sine of 30 degrees, again, there should be another value of this. Sine of 30 degrees means that. If that's the case, let's see how much you know of cast rule. What is the sine of 150? What is the sine of 150 degrees? People need to work on their cast rules a little bit more. Sine of 150 is as if we are creating the same triangle with a reference angle of 30, but in quadrant 2. Sine of 150 is also half. In the same way, what about this one? If I rotate 210 degrees, I'm essentially creating a triangle of 30 degrees in quadrant 3. So the angle of 210 gives me -half. And lastly, if I were to rotate all the way around for 330 degrees, it's as if I'm creating the same triangle of 30 degrees in quadrant 4, which gives me a value of a half, but a negative. And you might guess those numbers are also going to repeat again and again because this is periodic. That's a half. That's a -half. That's a -half, and that's a half. Shall we continue? If we had a 60, this would be root 3 over 2. And as I come down, it would be root 3 over 2. This would be negative root 3 over 2. This would be negative root 3 over 2. And you can plug it in too to get the same numbers on a calculator. The calculator would, I think, would give you 0.86 or something, 0.866. Okay, this is negative root 3 over 2 and negative root 3 over 2. Let's plot it. The points between 0 and 90 degrees is half and 0.86. So 30 is half and then 0.86. So it's very close to 0.9. When I come down, it hits 0.86 first and then 0.5. So it would be about here and then halfway. I think you'll believe me in saying that we do have a nice curve. It's not a straight line for sure. And if that's the case, now that you believe me, I hope, with this curvature, we're trying to create a circular motion. For the 3 dots here, just cheat a little bit and try to draw a nice curvy semicircle without even drawing the points. The goal for this section is to become so comfortable with these accuracy points at these dots that you can sketch these within seconds. So as a tip, here's what I would do. Okay, I'm gonna ask, I don't know, Carson, you with me?
Yeah.
Okay, let's pretend I'm starting my curve at 0, 0. Where does my sine curve finish after one cycle? How many degrees do I have to rotate to finish where I left off?
360.
360. I'm going to put a dot right there. Somewhere in between, when I start here, somewhere in between, I have to hit the midline again before coming back. And so my dot has to be right in between it. And then between the first two dots, I hit a maximum. And so I need a dot here, and then I need a dot here. What I'm trying to show you is, if you're drawing a curve, all you have to do is figure out where I'm finishing one cycle, and then dot, dot. I have a dot in the middle. I have a dot as a maximum between the first two dots. I have a dot as a minimum between the last two dots. And then you have your sine curve. All of this chart work that we're doing, we're just doing it to prove where the dots are supposed to be. But when we are sketching it, I like you to get this comfortable. I'll do this one more time. Okay? And this is my goal for you. If you have the axes, tell yourself, okay, in this particular question, what is my period? Assuming I start at 0, let's pretend I finish at 360. All right, what's the halfway mark? Oh, 180. What's half of half? So if this is 180, what's in between the first two dots? That must be 90. What's between the last two dots? Must be 270. Nice curve, nice curve. I'll draw it one more time with a different number, but that doesn't change anything. Here we go. Kiara, give me a random number from a random large number.
102.
108?
Two.
Sure.
Two.
102. Okay. 102. Let's pretend for whatever reason the period of 360 was shrunk or was compressed to 102. But I don't care. Why? Because I know that there is a point right in the middle between 100, 0 and 102. So take 102, divide by 2. That's 51. And I also know there's a max between the first two dots. So what's half of 51? 25.5. And then from 51, add another 25.5. That's 76.5. I have a minimum. It's as easy as that. Because I know that it has to follow a circular pattern, a wave pattern. Any questions about the sine curve? And by default, we do simplify so that the radius equals a 1. The radius could be anything, but when you plug it into the calculator, by default, they will reduce it to the lowest, easiest number possible. So it could be 1. But of course, that 1 changes if the radius was not a unit circle of 1, but the radius was like 100, of course, the maximum height would be 100. Just wanted to, mention that very quickly. But for now, we're just going to deal with the value of 1. Any questions? Okay, let's complete this. I want to do cosine law a little bit faster because it's basically the same thing. I'm rotating around. And then I want to show you tangent, although you will not be tested on it. let's clear this idea and let's move down. I'm going to move a little bit faster here. Cosine, if you remember, starting from the point 1, 0, cosine of theta is actually x over r. Assuming that we're in a unit circle, cosine of theta tells me the position of my x value in a circle. So when I am at 0 degrees, my x value here is 1. When I rotate 90 degrees, my x value is 0. And when I rotate around, my x value here would be -1. And when I rotate 270 degrees, my x value will be 0. And then when I turn a full 360, my x value goes back to 1. Notice it's a little bit different, but still has the same wavy pattern as the sine curve. Okay. So that's 90, 180, 270, 360, 90, 180, 270, 360. I go up to 1, I go down to -1. So this time, just to save us some time here, I am actually just going to focus on one cycle. Why? Because if you can figure out one cycle, you've figured out all the cycles. So let's just focus on doing the details of one. I am starting my function at a maximum, and then at 90 degrees, 0, and at 180 degrees, -1, back to 0, and 360, I go back to my maximum. And we're still following the circle phase. So from 0, it's going to be half, half, -half, and -half. This is, again, half with half. Oh, true. No. Half, and then I move on to the negative direction, it's -half. And I come back from the negative side, it's -half, and then +half. And then this is +half, -half, -half, +half. I think you get the point that we're using the same numbers as the sine curve. In terms of shape, it's identical. But what is different about this one compared to sine? The starting point. The cosine starts at maximum. I know that's a little weird because on a circle, we're starting on the x-axis. But remember, I'm taking a look at what is the value of x, right? The x-axis here is the angle that I rotate, and the y value here is essentially the value of x coordinate in the coordinate. So that's how it's programmed. Sine function is looking into the y value of my circle. So it starts at the center or the mid-axis. The cosine function always begins at a maximum and continues a sinusoidal wave. And while you might be copying that, I'm just going to fill in this chart. This would be √3/2. That's a -√3/2, a -√3/2, and a √3/2. And while you do that, I'm going to go back to my attendance. Let's see. F2. Josh, are you here? Nope. And Zane T. Both not here. Okay. Any questions so far? No? Okay. This is going to be a good opportunity for me to introduce the assignment to you. So, give me a second. This is, oh, it's already there. This is our assignment. Let me clear. It's very simple. You know the graph that we just drew? I want you to draw a very, very detailed version of the graph. Here's what I'm looking for. Just give me one cycle of sine or cosine that we just drew. But I need you to have a minimum of 36 accuracy points. In other words, every 10 degrees I want a dot. The whole purpose is, again, I need you to be so comfortable with the curve that as I did before, if you have a curve like that and I tell you some information, you'd be like, oh, here's my dot, that must be my dot, that's my midline. Bam, here you go, Mr. Kim, that's my curve. Like, I need you to be really comfortable with drawing those curves. So to convince you of the curvature and for you to get used to it, I want you to give me one cycle of sine or cosine on grid paper. If you don't have grid paper at home, you can take some from me in class. I want this to be done as soon as possible so that you can get rid of it and you could use it as practice. Here are the 4 marks that you're going to get. Here are the 10 marks that you're getting. The first 4 marks comes from the accuracy points. Did you not make a mistake with the accuracy point? You'd be surprised at how many people make mistakes drawing these points, all 36 of them. Okay. Number 2, conventions in vocabulary, things like make sure the axis is labeled properly, right? This is an angle theta, and here are all the degrees in terms of like 10 degree, 20 degree, 30, 40, 50. Here is your y value. It should technically just go from 1 to -1. Did you give me a title? Just, is it labeled correctly? Things like that. The last 2 marks come from artistic creativity. You don't have to be an amazing artist to do well on this. I will give you 2 marks as long as you put in any kind of effort. But just to give you an example, I kept some of the best ones that I've received over the last handful of years. And don't be scared, you don't have to do it in this caliber again. These are some of the best ones that I kept because I really like them. Here they are. Okay, take a look. So this was my best one, a prize student by far. She really went all out on this. Okay, that is a sine curve, and it is labeled correctly. She has 36 points, 1 point for every 10 degrees. I like that. And then she told me what function it was, f of x equals sine x. Yeah, everything's done. 4 marks for the accuracy points, 4 marks for labeling axes and the title and all that stuff, and then 2 points, obviously, for the artistic creativity. Okay? Yeah, but these are mine. I saved these. These are mine. Okay, these are my students. I still remember all of them. Here's another one. This one was pretty intense too. There's a lot of detail in here. 10 out of 10. Someone went Mushu, I think, on me on Mulan, the original Mulan, not the live action. Pretty cool. Gotta hand it to them. Here's some other ones. Creative. This person gave me 2 because they wanted to, have a terrain for their image. So as opposed to giving me, an accuracy point every 10 degrees. They gave me an accuracy point every 30 degrees. That's fine because they went an extra cycle. Here's another one. I thought that was pretty creative too. These are some really, really nice ones. Okay? Again, you have to go out of this caliber? Absolutely not. But show me some effort, you'll get the 2 marks. Okay? So that's the assignment. Quick 2 marks. Any questions? Going once, going twice. Okay, if that's the case, I want to go back to this. Oh, are those posted in Classroom? They will be. They will be. I just make the PDF just now as you were waiting for me to start the class. Okay. So consider this, right? I need you to be very comfortable with sine law and cosine law. Sine and cosine functions to the point where if I ask for sine, in your head, you'd be like, oh, it's this one. What am I going to do with this one? What are we transforming it into? If I talk about cosine, you'd be like, oh, it's this one. What are we going to do with it? Like I need it to be very quick in your head so that you don't feel, you don't lose any time or you don't delay yourself and waste time. Okay? If you can get this or this, both rather, all that's left is to apply AKDC and we learn about transformations. Once that happens, then anything that is periodic, you should be able to model using an equation. That's what we want to get at. Okay? Final one. This one, please put a little note in saying not evaluated. You are not responsible for this in my classroom, but me being a greedy, selfish math teacher, I do not want you to fall behind or be oblivious to this compared to other students, right? Why should my students know less than other students from other schools? Okay, so I'm selfish for you, and so I want to show you. You don't need to test yourself on it, but you should be aware that something like this does exist. So if someone's like, yeah, we have to learn tan and we have to get tested, you'd be like, not a big deal. Okay. Does this assignment have a due date? It does not. However, if you take a look at my calendar for our course, our quad, this Thursday, I'm also giving you another small assignment. So it's going to start ramping up. As we approach the end of the quad, I'm going to throw lots of evaluation and assessments at you in hopes that it will not only keep you on your toes, but also give you more opportunities for marks. So get it done as soon as possible. Don't be greedy for the artistic merit portion. Just do what you can and get it done. Okay? So going back, this is me being greedy and being selfish on behalf of you. I'd like you to think about it, and this is how we're going to end today. Tangent. Tangent can be written as sine theta over cos theta. So, being a fraction, when is tangent undefined?
We're
Someone?
still looking at a picture of the art thing.
Oh, are you serious? My bad. That's my bad. There you go. Okay. So, tan function. Jeez. Tan function. Um, tan can be written as sine x over cos x. When is a tan function undefined? When is this undefined? When x equals 0. Oh, there it is. Ian's got it. A fraction is undefined when the denominator is undefined. So a better way to say when is tan theta undefined is when is cos x equal to a 0? You remember? When is the x value equal to a 0? When is the x value equal to a 0 at the angles of 90 and of 90 degrees and 270 degrees? So this is going to be undefined, 270 is undefined, and as a repeat, the negative 270 is undefined and negative 90 is undefined. So let's draw quickly axes. Let me erase this. That's going to be, I think, what I did for the purpose of showing a nice clear drawing. I think I made each box, come on, silly ads. I think I made each box about 30 degrees. No, two boxes is 30, 60, and 90. So I have an asymptote here. 1, 2, and then 180. And then 1, 2, 270. I have another asymptote here. And then negative, negative, negative 90. I have an asymptote here. In other words, asymptotes repeat every 180 degrees. Okay, following. Let's see. When is tangent equal to a 0? When is this fraction equal to a 0? Tangent of x is equal to a 0 when sine of x is also equal to a 0. So what angles give sine of theta equal 0? Let's use green. It is when x equals 0. It is when x equals 180. And of course 360. And that continues to repeat here and here. What I'm going to do though is because you might have imagined that this is going to be again periodic, I am going to focus on one cycle and you will see it repeating again and again and again. So I'm going to go from negative 90 and go to positive 90. And I'm going to try to draw you the curve here, and then you're going to sort of cheat and copy it to all the other curvatures. All right? So I have when angle is 0 is here. So if that is a 0 right in between the two asymptotes, I know it's also going to be a 0, 0, and that's going to be a 0, 0. Okay. Next thing I want to see. 30 degrees and 60 degrees is all fine and all, but there's a special angle where sine and cosine are equal to each other. Remember how sine 45 was root 2 over 2? And cosine of 45 is root 2 over 2. So sine 45 divided by cos 45 is the same as root 2 over 2 divided by root 2 over 2. That means at 45 degrees, this equals 1. At between 120 and 150, so in the 135, that's going to be a negative 1. And between here, 225, it's going to be equal to 1. It's going to keep on repeating. So negative 45, let's just fit in a negative 1 there. So all the values where cosine and sine equal to each other will have a value of 1 or a negative 1. If I'm going to plug in 45 degrees, remember this is 30 and 60, 45 degrees is perfectly in the middle. That has a value of 1. And a negative 45 has a value of negative 1. You may feel tempted to just draw a straight line, but you also got to recognize that that dotted line is an asymptote. A tan function, as you get closer and closer to the asymptote, will increase in value, or on the opposite side, it will decrease in value. A tangent function looks like this. It's like a propeller. And this function right in the dead center repeats itself again and again to the left and to the right. This is a tan function. So again, 3 boxes and then -1. 3 boxes and +1. It does something like that. And then -1, +1. It does something like that. I went really fast for this one because I told you that you're not responsible for it. But I want you to see the relationship tan has with sine and cosine, and in doing so, it results in asymptotes. Okay? It results in what is it? Certain values where it actually does equal a 0. And because this is cyclical, as opposed to repeating every 360 as it divides, it will actually repeat every 180. So tangent is a very interesting curve. Will you ever use tangent, or is there ever a reason to use tangent to model something in real life? Very rarely. You may use it for very, very, very specific subjects, but when it comes to applications of real life, it's not that common. And so that's why in grade 11 we don't say you're not necessarily responsible for it. Some teachers are like, oh, it's part of the same thing, go do it. But we're trying to be as close to the curriculum as possible. Okay? So just know that this exists, know what it looks like, but your assignment is strictly based on sine or cosine. Any questions? No? Okay, then um, I believe at the bottom, at the next page, there's a bunch of sort of just busy questions that I ask you so that you would get that much more comfortable. Even though it might be redundant, I want you to go through it because these questions force you to think about certain relationships that cosine has with sine. Please try to go through them as well as work on the homework. Here's an example, right? Um, like the maximum y value is reached by the sine curve is what? What happens at x, and you just ask you to list them all. When does a sine function equal 0? And you start listing all the different angles. You're like, oh, it repeats every x degrees, right? Same with the cosine. When does a cosine function equal 0? Oh, it repeats as well, but it's different from sine curve. I just want you to notice these. So take some time to solve these and answer them like carefully. Here are some practice questions along with some textbook questions you can try. The pages following is just a summary that's straight from a textbook that tries to describe even the domain and range and just certain relationships that sine and cosine curves have with each other. By tomorrow, and so you have homework, everyone. By tomorrow, I need you to be so comfortable with sine and cosine that you are willing and able to draw a sine curve using just 5 accuracy points. Doot, 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 and doot, doot, right? In that way. And then move on to and be ready to transform them if I give you A, K, D, and C. Okay, we're going to slowly enter into AKDC using these 5 dots or these 5 dots as your parent function. Questions or comments? Okay, if that's the case, I'm going to leave you here. There's nothing else for me. You are officially dismissed. I will stick around for a little bit longer if you have any questions for me, at which point ask them now. Otherwise, we will see you tomorrow. Be ready for chapter 5.3. It's not a long lesson, but it will test to see how comfortable you are with AKDC from chapter 2 and chapter 3. Oh, another reminder, if you haven't done so, please do the quizzes. Some of you have a lower mark than necessary because you are not doing the quizzes that are free marks. Would you please just do it? Okay. Ian asks, in the 4.6 worksheet, what is number 4 asking us to do? 4.6 worksheet. Oh, don't worry about number 4. It was just an example of how this can even be used with, was it exponentials? Yeah. Don't worry about number 4. It was just an example. Okay. With that said, I'm going to stop recording here. Please make sure you give it a shot. Don't wait until tomorrow. Please get comfortable with sine and cosine function.